Hey guys, welcome back. So we made it through the less than exciting error calculation section. Now let's start doing our first method, which is the bisection method. Now this is going to be a bracketing method that's going to be used to find a numerical solution of something that looks like f of x equal to 0. All right. So that's what we're going to be doing. Now f of x here, that is going to be a continuous function. All right, so it's got to be continuous. This is an S here. So it's a continuous function, and it's going to be defined on the interval AB. Now notice we've got those closed brackets again, so remember we talked about that in the last video. When we've got those closed brackets, it's a closed interval, and that means x can be greater than or equal to a and less than or equal to b. Okay, so we're in that closed interval with f of a and f of b having opposite signs. Okay, so let's see what that means. So for this, let's just look at this example. So I just kind of plotted this out as just some random function. Notice that we cross the x-axis here. What we're going to try to do is get an estimate of this x location, because that would be the solution to f of x equals 0, right? So if we had our function and we found this x value, if we plug that x value back into our function f of x, it should give us 0 or very, very, very close to 0. All right, so the closer to 0 we are, the better. That means our solution was more accurate. Okay, now if you notice, I've got one end of the function here, one end here, and that's because if we add some things to this drawing, let's say this point right here is A. All right, so we've got A, and here's B. All right, so we've got those. So these are the endpoints of our interval. Okay, so this point right here is going to be f of A, and up here we've got f of B. So notice up here we said f of A and f of B will have opposite signs. So if you look down here, f of A is in the negative y part of the axis. So this is going to have a negative sign. Up here we're in the positive y values. So this one has a positive sign. So your endpoints, when you plug those numbers into your functions, you should have different signs. Okay, so you can't have both of them be positive, because then you'll never cross this x-axis. Okay, so keep that in mind, and let's write here that this point is the actual or true solution. So that's what we're trying to estimate. And this curve here is f of x. And remember, f of x represents y, right? So now we've got that. So let's go over what this bisection method does. And to do that, instead of having a here, let's set this equal to a1, and let's set b equal to b1, just to get us started. Okay, so if we do that, we need to add ones here, just to be consistent. Okay, so what we're going to do is we're going to look at an interval. So let's draw some lines right here. Both of these are directly under the lines you see drawn. So this is A1, this is B1, okay? And we're going to have this interval, or this bracket, and what we're going to do is we're going to find the midpoint, right? So let's just say it's right here. So this will be our first estimate of the numerical solution. So I'm going to put x in S1. Remember in the previous video we said x in S would be the numerical solution. This is my first estimate of that numerical solution. So we're just finding the midpoint of this bracket. All right, so now that we have this, we're going to create another bracket. So now let's draw one right here. So we're going to start at A and we're going to go to this new midpoint location right here. This will be called A2. Let's call this B2. And then this one in the middle again, this will now be our second numerical solution estimate. Now you might be wondering how I knew to go to the left and use this left-hand side from A1 over to X and S. So why did I use this side instead of over here? Let's talk about that. What you're going to do is you're going to use these values that we had above in this first bracket, and we're going to see if f of A1 times f of X in S1, we're going to multiply those together and we're going to see if they are positive. Okay, so let's put an if here. So if this is the case, so if f of A1 times f of X in S1 is positive, it's greater than 0, then what we would do is we would set the new A value for our new interval. We would set that equal to the numerical solution. Okay. Otherwise, what you would do is you would set B equal to the numerical solution. All right, so if we look at what we have here, let's go over that. Here's A1. I already know if I plug A1 into my function here, I have a negative number. X in S is up here, so that's a positive number. So I've got a negative times a positive, which gives me negative. So this, obviously the statement here doesn't happen, right? Because we're not greater than 0, we're less than 0. So that means we're going to set B equal to the numerical solution. All right, so here, see where I moved the ending of the interval? Now it stops at the numerical solution. Okay, and we start at A2. All right, so that's how I picked this left-hand side. So now what you would do next, you would do the same process. So now we would look at this bracket. All right, and now we would select a new bracket. So this time, let's just say it ends up over here. So this would be A3, we got B3, you find the midpoint. So it'll be X and S3. All right, and you just keep moving in and you're getting closer and closer. Notice how your brackets are going to get smaller and smaller each time. And each time you should get closer to this actual solution. All right, and the brackets again are determined by looking at the sign of this product right here. Okay, so that's what we've got there. And you can see here, if we do f of A2, well, that's still right here. F of X in S2, that's going to be a negative value. So we've got two negative values, which makes it positive. So A for our new bracket gets set equal to the numerical solution. All right, so that's why these two are directly, the same value. And then we use that right-hand side. All right, so that's kind of what that method does. So it just creates a smaller and smaller bracket each time until you get within your error. Okay. Now, let's talk about something else. So the original interval is sometimes given. All right. So sometimes you'll be given, you want to search on the interval from 1 to 3. Okay, you'll be given that sometimes. I mean, the textbook problems, you're usually given that. And if that's not given, you have to kind of try to figure out what interval to look at. So a good thing that you could do, if it's possible, is you could try to do like a rough sketch of the function and then kind of try to guess what interval you should use. All right, so what you'd want to do is you want to plot that function and then kind of locate where you think the root might be. And then, you know, estimate your interval. Now, if you're doing this in a numerical analysis class, like I said, usually the interval's given. All right, because they want everybody to use the same interval. It's easier for grading that way. Otherwise, everybody gets something different. Okay, but that's basically the method right there. All right, so let's go ahead and we'll stop this video here. And in the next one, we will talk about the algorithm. And after that, we will do an example. All right, see you on the next one.